Good evening. Yours truly, Professor Dr. Dolphy Gilpin, and I'm here today on the amazing 10 by 12 matrix. And I've been over the amazing 10 multiplied by 12 matrix. And we have two forms of this 10 by 12 matrix. One, the mathematical aspect of it, and one, the chemical aspect of it. I'm first going to go through the chemical Amz 5 by 12 matrix, in which it's a relative of the periodic table. Yeah, a relative of the periodic table, having 120 elements, with the last two being onium, which is 119, and 120 owned by nilium. But let's construct or design our 10 by 12 matrix here. So we have now, we're going to have 12 elements going across, 12 columns, and 10 rows. So let's see here now. Let's try to get a sort of a uniform interval here. So this would be about 5. So it has to be more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have an approximate interval here, and this will be 1. So after you know helium, hydrogen, let's get 12 across. So here will be 6. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, and magnesium. So we have 12 columns going across. And now we're going to have 10 rows coming down. So in this row, let's see, we have 13 with aluminum. So 14 would be wonder if we should have put the aluminum here and come like so. Let's do that for the first. I mean, we have done it like this most of the time, but let's do it this way. So 13 will are right beside 12 here. So we have aluminum. Silicon. See, that's why I call it a relative of the periodic table, because now we don't have sodium, potassium, and in the alkali group, we don't have the alkali group in the same group as the periodic table. So we can't call it the periodic table. That's why I call it a relative of the periodic table. A 10 by 12 matrix with 120 elements. So we have silicon 14, 15 would be phosphorus, 16 would be sulfur, 17 would be chlorine, 18 would be argon, 19 would be potassium, and 20 would be calcium, 21 scandium, 22 titanium, 23 vanadium, and 24 chromium. Once again, this matrix I designed doesn't keep or maintain the group properties and the row properties and the column properties as the normal periodic table, and therefore we cannot call it the periodic table. I just say it's a relative. It does have consecutive number of the atomic number, but it doesn't have any direct properties in the group and the rows. So we can call it the periodic table. You know, this is a 10 by 12 amazing matrix. I've used it. I'm going to also include quantum electronics, which is the sort of a physics of electromagnetic, the interaction of electromagnetic radiation and matter. And they use it in design of masers and lasers. So that's quantum electronics, and we know quantum physics and quantum chemistry. So we're going to use this one. My personal relative of the periodic table, we're going to use it for that. So here we go. So we come back here, so we have, this is chromium, so we reach now 25. That's manganese. 26 is iron. 27 is cobalt. 28 is nickel. 29 is copper. 30 is zinc. 31 gallium. 32, this is chlorine here. 17. Germanium. 33 is arsenic. And this is a very toxic element. Very, very toxic element, arsenic. 33 atomic number. 34 would be selenium. 25 bromine. And 36 krypton. All right, 37 would be rubidium. This is the audio I'll read for that, but I'll find out if there's any when they come on. And the other one, 38 will be strontium. 39 will be yttrium. 40 would be zirconium. 41 well, a more olden name for it would be pelopium, but I think a more modern one would be niobium. So I put here P-E and B. Pelopium, more olden time, that one is all they ever use, pelopium and niobium. So that's 41. 42 would be monobellium and B. 43 would be technetium. 44 ruthenium. So it came in two use. So one of them here, strontium and rubidium. This is ruthenium. One of them is probably RB and one is RU. Ruthenium. We're going to confirm that these two are 43 would be 38, 39, 40, 41, 42, 43, 44, 43. Let's go ahead. This is 39. Krypton is 36. So this is 37. Rubidium, probably RB. This is strontium, 37, 38, 39 yttrium, 40 zirconium, 41 niobium, 42 monobellium. For the tree, technetium 44, ruthenium. With RU for this one, and RB. 45 would be rhodium, RH. And 46 would be palladium. This is 13 over here. '23 vanadium and 24 chromium. 25 manganese, 26 iron, 27 cobalt, 28 nickel, 29 copper, 30 zinc, 31 gallium, 32 germanium, 33 arsenic, 34 selenium, 35 bromine, and 36 krypton. 37 rubidium, 38 strontium, 39 yttrium, 40, 46. 47 would be silver, Ag, and 48 would be cadmium. Notice we could have added the 30 on this side, but I just changed it up, really. Sometimes I do like to make a jump from way over here to way over here, so we have this one here. But nevertheless, whatever case we choose, it's not going to maintain the properties of the periodic table with the rows and the column, with the column as special groups, with the properties of every element in the same group have some similarities of the properties, but it does maintain the consecutive order of the atomic numbers. So here we have now 49 would be indium. 50 would be tin. 51 would be antimony. 52 would be tellurium. 53 would be iodine. 54 would be xenon. 55 cesium. 56 barium. 57 lanthanum. 58 cerium. 59 60 neodymium or neodymium ND. This is 58 cerium. 59 I think is praseodominium. Let's see. Yeah, 59. Praseodominium. 60 neodymium. 61 promethium. 62 samarium. 63 europium. 64 gadolium. 65 terbium. 66 dysprosium. 67 ulmium. 68 erbium. 69 putmium. 70 terbium. 71 luthium. And 72 afnium. Okay, so let's continue. So 73 tantalum. 74 tungsten. 75 rhenium. 76 osmium. 77 iridium. 78 platinum. 79 gold. And the atomic number for this is 197. I have to remember that because gold is gold. And I have to remember silver as well. Silver AG 47, let's go for 47. We have 107 here, 108, and 109 atomic weight isotopes. Gold doesn't have any isotopes here, just 197 atomic weight. 88 would be mercury. 81. Titanium. 82. Lead. 83. Bismuth. And 84. Polonium. And 85. Acetine. 86 would be radon. 87 would be francium. 88 radium. 89 actinium. 90 thorium. 91 protactinium. 92, uranium. And the atomic number of uranium is 238, atomic weight. 93, neptunium. And here we go, 94, plutonium. And the atomic weight of plutonium is 231. '95 is American. Like America. 96 is Curia. '97 berkelium. 98 californium. 99 einsteinium. 100 is fermium. 101 mendelevium. 102 nobelium. 103 so this one is for this one before this one is for this one. 103 is lawrencium. 104 is rutherfordium. 105 is dolphynium, dB. 106 symposium. 107 Orium. 108 is Asium. 109 is empty. Mechnerium. 110 non-satium. 111 rangium. Rg. 111 atomic number. 112 copernicium. 113 neorium. NH. 114 flavorium. 115 moscovium. 116 livermorium. LV. 117 tennessine. 118 organism. 119 on, enium, and 120 on by nilium. So there are our specialized 10 by 12 chemical matrix with the chemical elements. And it's in consecutive order of their atomic numbers. However, it doesn't maintain the group properties like the periodic table. So we can call it the periodic table, it's just a relative of the periodic table with the 118 plus 2 elements. And for me, this has been more convenient, but when you get in your exam, you better have your periodic table in order as the periodic table with the groups and the row properties and so on. Like this one would be group 1, and that's with hydrogen. The other one would be you have an alkali group or you have an alkaline group, and you have a lot of metalloid groups, and usually this would be the rare gas or the noble gas group on this side here. And you have the halogen group with chlorine and bromine and acetylene and iodine and so on. And all of those groups have similar properties with the elements, and it's with valence electrons properties and things like that. But this is a special consecutive order. The atomic number is maintained, the consecutiveness, and for the first 20 we usually just double. Let's put in the atomic weights. This will be like 1.0001. This will be approximately 204. Do that hydrogen as 2 isotope, do 2 rhodium and tritium. They call them heavy hydrogen. One with same atomic number but different atomic weight. Right? And so we have lithium here would be 3, approximately 6 here for the atomic weight, approximately 8. Good approximation for the first 20. This was approximately 10, approximately 12, approximately 14, and this is approximately 16. And we know that oxygen is really 15.9999. That's another one to have to remember, because we know that the intrinsic gas element there for life, oxygen. So you notice some specialized elements. I know I maintain both the weight and the atomic number, like gold and silver, oxygen. Our fluorine would be approximately 18 here, and usually it's 18 plus, except for this one is a double and then minus, because this is 15.999 by spectroscopy. And it's approximately 20 here for the atomic weight. Approximately, we know this is about 23 because sodium, is one of those popular elements. Put it in water there, put it on, and it runs, burn with a blue flame, and it's volatile reaction on water, relieving hydrogen. So we know this is 23, so that will be 22 plus. Let's put 23. So you double it on your plus. This will be 24 plus. And so on, the first 20. And you could double all of these for the atomic weight and plus, but the more after the 21, the more the interval of the doubling after the doubling is more, sometimes much, much more. In the case of the first 20, you might have fractional and probably one digit, but afterwards you find out that, for example, let me see if I could find one. Yeah, gold. 79, if you double gold, you'll get 79 and 79, 88, 160, 158. So it's 158 plus, but it's 197, so it's much, much more than the doubling. But over here, it's just sometimes by fraction or by unit. Same thing with silver, Ag, silver. The atomic weight of silver, 47 is the atomic number. Let's do for Ag 47, 30, 42, 47 silver. So if you double silver here, you get 94, but you notice that the atomic weight is 107, 108, 109, and those are the isotopes. So it's much, much more than the doubling as we come down with it after the first 20 elements. So here we have the Amz10x12 specialized matrix, and this is for chemical application. And this will maintain the properties of the stem and the steam and stream for the Amz 5x12. The other one we use for economic output, infinity output, exponential output, and much, much more. For example, in engineering, we use it in circuit analysis to design circuits as well as to solve the circuits by matrix or matrices analysis. Okay. So this is for chemical application. It's a specialized Amz10x12 chemical application here. And the other one will be more for stem, steam, and stream. And you know what all of that means. I'm not going to go over that today. So there you have it, the Amz10x12 specialized chemical matrix. A 10x12, which give us 120 elements, and the last two be owned by Nilium and Enium, 119 and 120. And another thing, sometimes you see we have to have 12, we have 13 here, but I think it's best, I've learned that in skipping sometime across here, sometimes it entertains mistake more easily than you just do this. We do this, you start here and you go here, and then you come here and you go so, you come so and you go so, come so and you go so. Yeah. So here you have it, our 10x12 matrix, and 120 elements for the specialized chemical application. Let's give an expanded view here. Matrix expanded view. expanded view, Amz10x12 matrix, chemical configuration, and notice I've dropped in all 120 elements mentally. So this is like me in high school being able to do the first 20, run it off, and keep it in my head. Here my at retirement age, and I'm doing the whole 120 elements with the atomic number and their atomic weights in approximation, atomic weights. Yeah. Only in specialized cases like also plutonium and uranium, those two I've learned because they are specialized elements. Uranium is 238 point, probably something 0.231, and plutonium is 231 point something as well, but I just have the whole number configuration for that. So that, and gold and silver, you know. Also for samarium, I have a special way to get for samarium because I did the professional engineering preparation for that. And one of the score was 68, and so for that I remember, I said 68 is always samarium, though 62 samarium, and the atomic weight for that is 158. And 68 was the score on the other professional engineering license preparation, and 68 is erbium, and the atomic weight for that is 168. You just drop a 1 in front of the 68, in front of the atomic number, and you get the atomic weight. That's for erbium. So there's a couple of them I maintain both the atomic number and the atomic weights.